In this episode of The Bear Roars, Dan sits down with Jeff Williams, CEO and CTO of Exum Instruments, to discuss how his company is transforming materials analysis with its cutting-edge Massbox technology. By making advanced elemental analysis faster, more precise, and more accessible, Exum is helping industries like aerospace, battery technology, and national security push the boundaries of innovation. Jeff's journey into tech was anything but typical. A rock climber turned geochemist, his passion for understanding materials took him from studying meteorites to rethinking how we analyze matter at the atomic level. That curiosity led to the creation of Exum, where he's pioneering new approaches to scientific instrumentation. He and Dan dive into the challenges of scaling a hard tech startup, the thriving deep tech scene in Colorado, and the role of AI in the future of materials research. Let's poke the bear to kick off the conversation.
All right, Jeff. I said this word 5 times before in my life, all in the past 30 seconds.
You're going to nail it.
Mass spectrometry.
Close
enough. So what is that? Tell listeners what that is. Why did I start this out with, you tell us first how to pronounce it, please, and I'll try to get down.
Mass spectrometry.
Yeah, you think I would know since I'm an investor in your company, but
that's okay. That's not the important part. So basically, our company, we make a tool to basically take anything solid and we can then analyze all of the atoms in there. So what I mean is how much lithium, how much iron, how much uranium. So mass spectrometry is the spectrum of mass that's created once we can filter all these things out. So I know, in a lot of your other shows in the quantum world, you're dealing with, using lasers to use photons to interact with atoms. We're doing something similar, but then we're actually taking all of those atoms and we're separating them out with electric fields, and then we're counting them by mass. So the best way to think about it is we have this material that has some amount of lithium, carbon, iron, uranium in it. And we want to, at every spot, remove those atoms. We want to ionize them because once we can ionize them, we can talk to them. So we can, push them and pull them with electric fields or magnetic fields. We can make them into.
All right, I'm going to back us up a little bit. And we're going to talk about why we want to do this and who wants to do it. But I want to kind of go back over what you just went through, and I want to start with maybe a next level up understanding of what you just took us through.
Sorry.
So you have a device.
Yep.
So maybe I'm putting this a little bit further along. You guys have invented a device. You've built a device that you can. What does it look like?
Yeah.
I've seen it, but tell the users what a device looks like.
So it's
as big as this room, is it as small as a little mousetrap? What's the size of this thing?
Yeah, so it's a desktop device. So it's about the size of 2 microwaves stacked on top of each other, right? And so this device has a touchscreen on the front of it. You put a sample in it, and we tell you all of those constituents.
So you're going to tell whatever that material is in there.
Yep.
You're going to tell specifically what atoms it consists of. So so walk us through again, just like you were, and maybe just go a little bit. I don't know if slower is the right word. A little bit more clear to someone who really wants to get a firm picture of what is happening. How do you able to take this? What do you do scientifically to it that tells you what the atom composition is?
Okay, cool. Let's do that.
And you were doing a great job before. I just know that.
Of course. No, I like
people are going to really want to understand this in order to kind of bring the conversation to full life.
Yeah, let me try to go to it like a higher level too. So when we take the big focus of like why we made this is we wanted to be able to take anything solid and analyze it, because the best way to analyze something currently is to do it as a liquid or a gas phase. It's very difficult to actually do mass spectrometry in the solid form. And so what we did is we take this solid sample, so it could be a piece of metal, piece of wood, plastic, a battery anode, whatever it might be. And we load it into the front of the machine. A little tray comes out. It goes into the machine.
How big does a sample tend to be?
Yeah, like it can be anything from basically 3 inches by 3 inches by like a 1 inch high maximum size, which is actually pretty large for our world. So this could be literally a whole battery anode that's cut up and put in there, for example. And so it goes under vacuum, and that's going to be super important because, again, we want to measure the atoms in that solid phase exactly how they are.
Mhm.
So the important part is if you're a researcher and whether you're metals or batteries, you want to know where are my atoms, not just like, do I have 50 weight percent iron and 100 ppm lead? You want to know, is my iron where I think it is? My lithium where I think it is? And so what we do.
And I want to come back later and say, why would I want to know where it is within that small sample size? So we'll come back to that.
Yeah, we'll come back to that for sure. So for the time being, let's say you made a new material and you're really happy with it, but you don't really know, what the secret ingredient that you came across is. Like, oh, was it the amount of gallium that I put in there or the amount of lead? So what our machine allows you to do is you put it in there and a laser is going to come down. And this is an ultra fast laser. So 4 picoseconds. So really fast lasers. And what it does is it basically ablates a little bit of material. So the way you think about this is like drilling with light, right? So if you can imagine drilling into concrete, it makes this dust cloud. That's kind of what's happening in the ablation. The ablation basically rips apart all the atoms at that really small spot. And by small spot, I mean, 10 microns to 150 microns. We're talking like fractions of a human hair here. So really small area. And when we make this cloud of dust, essentially from the ablation, it's mostly neutral atoms. And when those atoms are flying up, we can't talk to them yet, right? They're just neutral. They're just flying up with, first principles physics. They're just going up in a cone. And so we need to be able to give them a charge in order to push them and pull them and manipulate them. So then we take another laser, which is another UV laser that's very high power. And what we do is we interact with that electron on the very outside of the atom and we excite it and then we excite it again. So we actually capture it before it falls back down. And you get it so far away from the nucleus that you have now an ion and electron pair. So now the electron's so far away, we can pull the atom away from its electron, and now it has a charge. So we deal with positively charged ions. But now you can imagine you have these ions that are just kind of spreading up in space. And we want a way to basically make this into a beam, kind of like the same way you make light into a laser beam. We want to make these ions into a coherent ion beam. And so the way that I like to explain this to people is you can think of ion optics very similar to, if you took a lens and, I'm sure everybody did this as a kid where they took the lens and focused it down to a small spot and burned an ant with it, right? You can basically create those same shapes of a lens with electric fields. And so we can actually pull the beam and focus it and defocus it and make it into this nice packet and pull those ions off to the side. And then we can kick them really hard. So we do this really high voltage push. And it's like kicking a bowling ball or kicking a soccer ball. If you give them the same amount of energy, they're going to travel with different velocities. Mm-hmm. Right. And so lithium, the lightest element that we analyze, we don't do hydrogen, for example. Lithium's going to go very fast and uranium's going to go very slow.
So it's more like the soccer ball than the bowling ball.
Yeah, exactly. Yeah. So lithium's a soccer ball. It's going really fast and uranium's going to go very slow. The lithium is mass 7, uranium is mass 238. Right. Mm-hmm. So huge difference in, velocities that's going to happen. And so basically the mass spectrometer side of it is the mass analyzer. It's what's actually separating these things out in time and space. And so our time of flight mass spectrometer, because it's the amount of time it takes to fly, basically we have a detector and we fly the ions in this U shape. And there's a lot of reasons for that. We could go into more detail, but we basically fly them in this U shape. It's like rolling a ball up a half pipe. They roll back down and then they hit this detector. And so when we're looking in time, we see lithium, then we see carbon, then we see iron, and then we see uranium. And then we can turn that time space.
And you did the order based on weight because the one is making it there quicker.
Exactly.
It's lighter than the next one and the next one.
Yeah, exactly right. And that's the beauty of mass spectrometry is because everything always has the same mass. Lithium's always going to be mass 7. Uranium's always going to, there's isotopes and all that, but they always have the same mass for their isotopes. Whereas depending upon in like spectroscopy space, when you're dealing with photons and how they're interacting with different electrons in different orbitals, you might have to look at things in different wavelengths depending upon what you're looking at, right? And so, but mass spectrums are very clean. It's, oh, that's definitely lithium. That's definitely calcium. That's definitely uranium.
And when is it right to think you're taking a sample by the first the first beam that hits, the first laser, kind of produces that cloud, but that cloud's from a really small sample. How do you know that sample is representative of that overall piece of material?
Yeah, that's a really good question. So this is like this is one of the powers of our technique, but also to what you're getting at is like, does that 10 micron spot represent a 1-inch area, right? And so what we're able to do is take that sample and it moves on a stage. And so kind of like an old CRT TV where, it kind of rasters the electrons like this, right? And and it builds an image. That's what we do is we move the sample shot by shot by shot. And then we take the mass spectrum at every single one of those samples. And then we can basically think about every spot has a mass spectrum, in this space. And we can say, let's look at lithium. And it'll take at every spot, it'll integrate the same peak for mass 7. And then it'll create a chemical image of here's where all of the lithium is. And we can actually like make a heat map of the exact lithium distribution.
Gotcha.
Yeah.
Good. Okay, so let's now talk about before you guys were doing what you're doing, what is the normal way of doing this? What's if you look backwards in time or even current, how it's done mostly today, how do people go about doing this, knowing what materials are in a sample?
Yeah. So, really like the inspiration of like why we're doing what we're doing is because, my background wasn't doing this work in cosmochemistry. So I did a lot of work with meteorites, early solar system formations, and I worked at the National Lab in Florida. And I got to use kind of the whole gambit of analytical techniques. And still the best way before we came around to do mass spectrometry, like quantitative analysis on solid materials, is to turn it into a liquid. So it's to take your rock, it's to take your metal and underpay a bunch of grad students to do a bunch of acid chemistry, a bunch of column chemistry, dilutions, and then put it through this instrument that can basically take that liquid and ionize it and then go through the mass spectrum. So it's a lot of work. And
like, take us through what you mean by a lot of work. I can, hours, days, one person, 4 people.
Yeah. So let's say, I don't know, Crusoe Ventures decides that they made a new alloy and they want to get it analyzed and they send it off for analysis. You're not going to get that result for like 3 to 4 weeks unless you pay a lot
of elapsed time.
Yeah.
You have to ship it away.
Yeah. Because you don't want to pay for the overhead of that machine. So it tends to be consolidated into central labs or universities. And then once you're there, you have somebody who's taking days worth of work to digest that sample. Sometimes you have to do chemistry to that as well because there's too much iron in it. So then you have to like remove just the iron and leave everything else behind. So that could take more days of work. Then you do all your preparation and then you finally get time on the instrument. And then it's going to take a whole day to kind of get your analysis done. And then it takes days after that to actually get all the way to a quantitative answer that you're confident in because you have to do a bunch of standardization. You end up with 3 different software packages that, you're still manually doing in Excel ultimately. And it's just kind of the way it's been done for a long time. And it's a tried and true method. It works, but it was never industrializable really. You had really big companies like your Siemens or your Northrop Grummans and these sorts of companies that would have labs that could actually afford the capital equipment, building a clean lab, paying for 2 to 3 PhD chemists just to run one, system, and then have enough dedicated machines to do whatever the work you wanted to do. They weren't very generalized. You tend to set up a machine to be like, this is my machine for doing quality control on aluminum. Just really good at that. Just leave it alone. And the same thing's true for basically any of those environments. It's figure out the method that works, leave it alone, and then pay somebody who gets really good at the chemistry. But then still, you're talking, weeks of time to get answers.
Mm-hmm. Yeah. So why are you doing this? You kind of give us a little bit of a snippet of you ended up doing this work in Florida, and that's where the idea came from the company. And we'll talk more about kind of what you're really doing and why you're doing it at the company. But what got you to Florida doing that type of work? Why was it so interesting to you, both to do in the first place, and even more interesting that you want to build a business and a career around creating a service and a product around it? What's your backstory?
Yeah. So my backstory was, I didn't have the traditional route into sciences of like, I always liked science as a kid, but I was never really like an A student in high school. I was more interested in rebuilding cars and engines and taking things apart, and kind of just had like a tinkering mindset, a maker mindset. And, school was fine. I was never really like super inspired, but, enjoyed certain aspects of it. And then I was a big rock climber at the time as well. So, going into late high school and early college.
Where was it you're growing up?
I grew up in Tampa, and then went to school at Florida State. So not really a great place for rock climbing.
Let's say, where do you rock out there?
So all indoors. So this is like kind of like when rock climbing gyms were just like starting to gain traction. So this was like, 2009, 2010. And so worked at a climbing gym, which was just like an old smelly warehouse. And as a function of rock climbing, I was like, I'm going to take a earth science class. And I had this amazing professor who just like was able to give science life in this way that I had never thought about before. And it gave meaning to all of these, disparate things. And I think geology and geochemistry is really this culmination of so many different aspects. I mean, it's physics, it's chemistry, it's mechanics, it's, engineering, all built into kind of this general science of like, really large scale processes like the earth, that you're able to then look at something on such a small scale, like a section of rock, and make a big story out of. So it's also super creative all at the same time.
Tell us more about the professor, and like how would he do that? How would he bring it to life? What's a story that he might have told?
Yeah, let me try to think of, it really came down to the labs. And I think what it came to is we would take this lab where it could be something that might seem super boring, right? Like if you take a section of rock and it's like cut in half and you see all these different minerals in it. And he would set up the lab such that it's like a geologist is essentially like a detective. And you're looking at this slab of rock, and it's like, okay, let's first start with, what's the hardness of the rock, and what are the different minerals that are inside here? So it has some quartz, it has some feldspar. But then notice that the minerals are slightly stretched or elongated. Like, what does that tell us? Oh, that's probably like some metamorphic activity that happened. So like the earth was having these huge stresses of like shear that were happening. So this is probably around a tectonic zone. And then it was, the chemistry of those minerals also tells us where they started from, and, down to such small amounts within the chemistry of the minerals, like down to, parts per million levels of strontium in here. And I guess what I'm getting at is you go like layer by layer by layer down. And by looking at something as small as like a 1-inch sample of rock, you can tell this huge story, right? You can look at the earth in that specific area, like, square miles based off of what the story of one thick section is telling you. And what I liked about it was you had to use chemistry. You had to think about how it was forming, how the mineral initially formed from magma and then made an igneous rock, and then had to go into a metamorphosis, and then, got moved around, and the chemistry changed here. And then also there's a whole math component, and gave math this light as well, that it really was the language of science for deducing these macro scale processes all the way down to these, micro scale processes.
So you know who Graham Hancock is?
No.
Well, Graham Hancock would love this stuff. Graham Hancock is, he's got a couple series on Netflix. He's big on Joe Rogan. He believes it's highly likely that civilization, began well before kind of our archaeologists believe it began, and then got largely wiped out during the lower Dryas, I think they call it, which happened around 9,500 BC. So it's kind of trying to look at history before this cataclysmic event, things that we think of as folklore like Noah's Ark, but stories of Noah's Ark all over religions and cultures, on a global basis. Something caused this mass event on Earth that caused, mass extinction of the woolly mammals and other very large species, all in a very short period of time. But he believes it also wiped out all but traces of kind of much more advanced human civilizations, not advanced by today's standards, but advanced by what you think of as a civilized, farmers and builders and artists that pre-existed kind of what we think of as maybe 5,000 BC or 6,000 BC by, maybe even 1,000 years and across the globe. But it's taking pieces of evidence that you have and trying to, use it to tell what stories might be behind it in a way that's consistent with evidence, but you don't necessarily know and will never know, how close you are to the right answer.
Yeah, I love that. I think it's fun because, you get to be really creative, right? You get to look, you have to ask yourself, how do I look at something a little bit differently that maybe starts to put all the pieces together in something that's not so obviously seen. A whole civilization being wiped out. How can you look back and see where that is? That's cool.
Yeah. So that got you going on the path of maybe I want to be a scientist.
Yeah.
I like material. I like testing materials and figuring out what's really been going on there. So how did that then lead to what you were doing in Florida?
Yeah. So I started taking, I was like, well, I like to climb rocks. Apparently I like studying rocks, let's, see where this goes. So that's a unique combination. Yeah.
I don't know if people like the rock climb, but maybe they like to study rocks too.
Yeah. Now I have a weird obsession of collecting rocks. So it's going to be great. So then that got me into starting to take math classes. And once I had a reason, all of a sudden,
what with math, what was your favorite part of math? What kind of math really got you?
Yeah. Which again, professor, I started taking math courses because I had to for going down the sciences. I was like, oh, I'm actually pretty good at this. And I like it now that I have a reason to like it. And then I took a Calc 2 class and everything just kind of clicked for me. It was just everything just, it was this retired Navy guy, or maybe it was Air Force, anyway, retired military, super strict, super hardcore, but so thorough and so caring in Calc 2, which, a lot of people hate their Calc 2 course, historically. It's one of their least favorite courses. And it was my favorite class. And it was all because of this professor again. He really it's I think Calc 2 was that moment where just so much math that you just kind of take for well, that's the equation for doing this. And now it's well, here's why it's that equation. And it gives you so much more reason to everything else behind it. So that got me going down that path. And I started to take more and more geology classes, deeper chemistry classes, and I really started to love it. And then the moment that set me down this whole mass spec instrumentation world was I took a tour.
Yeah, why couldn't I have just said mass spec instead of that longer version of the word? That's easy.
Well, I wanted you to struggle.
Thank you. Appreciate that.
What really took me over the edge and set a lot of my trajectory was I took a geochemistry. It was a earth science, environmental science course. And the teacher of that course was the head of the geochemistry department at the National High Magnetic Field Lab, and takes us the whole class on a tour. And I just see these instruments that are just the coolest thing I've ever seen, right? It's the whole traditional science lab with, things you just have no idea what they are, and all sorts of equipment everywhere. And there's plasmas that are doing something. And I didn't understand any of it, but I just knew in that moment. I pulled the professor aside after the tour and I was I want to work here. And he was I don't have any opportunities. I don't care. I will work for free. I will take the worst job
Work
possible.
For free. There's an idea.
Yeah. I will do whatever it takes. And he was sure, we'll see what we can do. And he gave me the worst job possible. I think it was a test.
Yeah, testing you.
He made me watch paint dissolve for hours. So there was a
He made you do what?
Watch paint dissolve.
Really?
Yeah. So there was a
It's
problem.
like a Karate Kid episode. Watch the paint dissolve.
And make notes on
I'll
it.
be back tomorrow.
there was a mission called the Genesis mission that crashed into Earth after basically collecting a bunch of solar wind, and it was actually because of like a negative sign in an accelerometer, so it didn't deploy the parachutes, and so there was like all this paint contaminant on the solar wind samples. And so he was like, well, figure out how to dissolve the paint. So I would literally spend weeks going into the lab in a fume hood and just staring as I would try different acids and different heats to get this paint to dissolve. And like once I passed that test, he was like, okay, now we can go do something else. So that's what kind of sent me down that.
Well, I would have lasted about a day or two. My equivalent is I had to watch ribs cook for some guy who was really good at ribs, but he'd have to cook them all day, but he didn't want to sit there and stare at them on the grill. And so my job was to stare at them on the grill. And when the fire started to burn too much, put some water on it. I'm like, how many hours I got to do this for? You're a better man than me. So you found your passion.
Yeah.
And then the other stuff he had you do in the lab, did they get more interesting?
Yeah. So then he was.
I'm assuming watching the paint dry wasn't all that interesting.
It was not that interesting. No, but I was like, I'm gonna be the best guy at watching paint. So then he actually gave me some really fun work and opened my eyes to cosmochemistry. So taking all the stuff I'd been learning in earth science and saying like, let's apply it to this meteorite record. Right. So we have all these meteorites from different parts of the solar system that, were all these planetesimals that had formed, in really early parts of the solar system that eventually like broke up and are now in our asteroid belt. And every once in a while, not every once in a while, pretty often actually, we get these little rocks that, land all over the world. We happen to find most of them in the Antarctic or in the deserts because they're really easy to be like, that shouldn't be there. So we go find a bunch of meteorites.
So when they say that shouldn't be there, like what would, this person stumbling across them probably doesn't really have, they're not looking for something that's not going to be there, but what is it about how they look that makes them look so out of place?
The landscape difference, right? And so now there actually are these explorations, but we'll go into that. But basically, if you're on a huge sheet of ice, like in Antarctica, right? And you see this rock kind of like sitting on the surface, you're like, probably a meteorite.
Mm-hmm.
Because it's like shouldn't be there because most of the rock coverage is just under snow and ice, and so anything that's kind of on the surface or near surface is like
there's no way for it to get in there other than dropping it from the sky,
or like in the middle of the desert, right?
Yeah.
And so now there's just like there's entire like cohorts of people in the desert. I think the funny thing in the meteorite community was like they started out hunting on camelback and now they hunt on and Range Rovers in the desert because they made so much money on the meteorite trade. And now there's like huge Antarctic missions and everything. And so, yeah, we have this.
So how did you make money on the meteorite trade? So I'm hunting for meteorites, find some. What do I do?
Yeah, there's huge amounts of collectors, right? But then even in, university and academic spaces, it's like this whole world where there's a lot of meteorites that are like literally called ordinary. They're ordinary chondrites because it's like, they're everywhere. It's kind of like these first solar condensates that came out of our solar nebula. And they're fascinating, but ordinary. But then there's these really special ones. And so you're kind of hoping that you stumble across a special one. Like we have meteorites from Mars, right? So we have like these known meteorites that something impacted Mars, blew off a bunch of material. That material then fell into Earth. And now we can actually study Mars. You get one of those, that's worth a lot of money. And academic
what does a lot of money mean?
I think more than platinum per gram, right?
Yeah.
Like more than any precious, metal.
Well, give us some numbers. You're a math guy. So how big of a sample might I find?
Well, that also ranges like you could find something like a boulder size. That's an entire iron meteorite. Yeah. And then like per gram, it could be thousands of dollars per gram of like just little bits, or like you could section it off and, sell certain like better sections to universities for thousands and thousands of dollars, and then you end up distributing it, and then those labs end up like doing some analysis on it, and then they'll sell it to another lab to do another analysis on it, and you get these kind of like really hyped meteorites. Like all of a sudden one comes across and it's like, oh, have you done the analysis on this one? And that one goes for tens of thousands of dollars. And then collectors.
And when they're doing analysis, are they hoping to discover a new material, discover new properties? Is there something that could come out of that testing that creates something of value, or is this just, people are curious to have a lot of government money to burn through.
Yeah. Yeah. So I think a lot of it's driven by who's going to have the hot paper because they're going to find something out about Mars or about the moon or something like that. Some novel aspect of like refining our understanding of the solar nebula. And then there are features, I would say, like that are like really important, let's say, for kind of like new space economy stuff. Like when we're thinking about like, let's say the platinum group elements and understanding like where should we go mine in the asteroid belt. So everything that's happening with OSIRIS-REx and all of those samples, like there are some really cool stuff for like future of humanity and creating a space economy. And ultimately, I think the reality is the most sustainable way for resources on Earth in like the super long term is in the asteroid belt or on other planets. Like, let's not mine here if we don't have to. And so I think a lot of that is understanding the full landscape of our solar system and where are the precious minerals. And also, we're talking about lunar bases and Martian bases, where do we want to be on them? And so the more we can understand about that sort of mineralogy of how do we make fuels, how do we make materials, what kind of, minerals are there, the same way you would on Earth.
What about finding exotic new materials? Does that happen at times?
It does. Yeah. So there are certain mineral phases that you can only find in meteorites. And sometimes like meteorites that aren't even from, our galaxy necessarily. So there are, but it's more academic, I would say, than like, wow, we found this phase that changed the world so far. But there's that opportunity, right? Because it's totally different environments.
All right. So now I'm going to ask the wacky question. Are you ready?
Yeah.
So in the UFO world or UAP world, as it's now called, there are people who will tell you that there's retrieval operations where there's some kind of evidence of a crash that they go and retrieve materials and then need to reverse engineer the materials. Has that ever popped on your screen, or is that I have no idea what you're talking about?
It's never popped on my screen, but if it does, I probably couldn't tell you.
Well, you can at least tell me that you can't tell me.
But I'll tell you what, my my mass spectrometer though, we could reverse engineer and tell you what it's made of.
All right. Well, I'm gonna get that to some of these guys who are claiming they've been part of those operations.
Tell them to bring it on by. We'll shoot it.
All right. Well, there's some stories I'm going to share with you offline on that because that's what they have to do at times, or so they claim.
Yeah.
Great. So now you're knowing what you want to do. You're understanding kind of very unique space. There can't be that many people who are really focused on that space. You're now starting to understand this is a really kind of time-consuming, resource-intensive process. Actually, before we go there, give us more, a range of practical reasons why commercial customers have a material that they want to understand. What is the atom composition of it?
Yeah, I mean, it's kind of foundational to almost anything you can think of, right? So if we're talking about polymers or we're talking about metals or, from taking the rock out of the ground or the ore and then doing the separations and then making it into the material that you want to make ultimately.
Or give us maybe give us a little bit more live world examples. Give us the type of company who's trying to do a certain thing and they're the type who would turn to you or someone like you to want to analyze the material.
I think the easiest example probably is let's take aerospace, right? Everybody can understand that like aerospace is constantly making these new alloys that can go hotter, that are harder, that are lighter, all of these sorts of like new alloys that are happening. And like we're getting to the point of the material science that alloy composition has to be so precise. And any amount of like impurities in it, or if the vanadium's a little bit too high, totally changes the properties in a way that could be like catastrophic for the plane.
There's in the latest as of the recording here, probably not the latest by the time we drop it, but the latest Joe Rogan with Elon Musk, which was last Friday, somewhere in the middle of it, they go on for 20 minutes with Elon talking about the heat shields, heat tiles, and how much precision is required, the material, how easy it is for something to go wrong. But until you get them all right all the time, you're not going to be able to reuse the rockets. But goes into excruciating detail as to, why the precision of understanding and experimenting with how to make it better and better is so critically important.
Yeah, and that is like a textbook example of what's happening now, like across the board, right? In material sciences, we're getting to this whole new level of materials that are super precise but are super amazing. But in order to get that super amazing quality or ability of that material, has to be perfect chemically. And so you want to be able to, if you're, let's say, Lockheed Martin, and you're making some new titanium alloy for some new fighter jet, you want to make sure that you have a process control of, okay, we found this material. It's very academic now. How am I actually practically going to make enough of it consistently enough that I can make a whole airplane out of it? And one, issue in quality control isn't going to make the whole thing just disintegrate, right? Like your heat tile example.
Mm-hmm.
And so that's becoming like exponentially more important. And what we're seeing, which is great from a timing perspective, we're getting a lot more interest from that sector specifically, because for years they've kind of been using a lot of the same materials. They'll send it out to labs. They don't really have a lot of these internal characterizations. They're like, oh, it's close enough. We've been doing it like this from the 60s. Like, okay, great. But now that they're starting to develop new alloys, new technologies, they don't have quality control processes for it. They haven't had 50 years of working it to know what it's doing. And so you want to be able to have that really micro level and macro level understanding of chemistry. And that's what like our laser, allows you to do, is you don't just take all the metal and get one number out of it because you digested it in a bunch of acid. You can look at it in space and say, how's it distributed? Is it homogeneous? Do I have these imperfections? Do I have these contaminants that show up from time to time? And what's that contaminant going to do? Or you find a contaminant in a test. So you make a test piece, you break it, and you find that 3 out of 10 of them are breaking under the yield strength that you want them to have. You throw them in our machine, and it's like, hey, by the way, you had too much oxygen there, or too much vanadium, and you have an issue.
So they're able to kind of, where it broke.
Yeah.
They're able to show you that sample. Okay, this broke. Tell us
what happened.
What's different there relative to
exactly
the norm.
Yeah. So we've been doing a lot of that work in the additive manufacturing space. So in metals, so actually with NIST here as well. So being able to kind of refine additive manufacturing on the chemistry scale. Now, not necessarily like a lot of people were just focused so long on like, let's make something out of metal and just get it to work. And now it's like, well, now let's get it to be consistent, being able to put into production, being able to be airworthy, flight worthy, these sorts of things.
Yep. Yeah. So take us through a couple other examples, different industries, different use cases.
Yeah. So one of the big industries for us right now is battery. One of the advantages our technique has is we can see the whole periodic table. Like I said, lithium to uranium. That allows us to do something that's never been able to be seen before for battery researchers, is where is your lithium, right? So we're making all of these new battery substrates. So from solid state batteries to silica anodes to even just traditional lithium ion. A lot of the times, actually most of the time, either you take the battery and you digest it and you get one number of how much lithium was there, or you can take other techniques and look at everything else but lithium. They can't measure lithium directly. And then so you're kind of doing it by difference and hoping that's the case. But we can now take a whole anode, map the entire anode once. And remember, I said that we remove a little bit of material. Well, we can keep doing that like 50 times. And now we can make a 3-dimensional reconstruction of where is your lithium? What's happening at top of charge versus bottom of charge? What's happening, battery researchers know that they have these issues with the lithium plating out or the SEI formation, but they've never really been able to truly directly measure it. It's very difficult. And so for the first time, we're giving battery researchers or even, companies that are trying to take something out of like a small production line to how do we get this to a gigafactory scale? And so that's been a huge industry for us, is showing people something they could never see before.
Mm-hmm. So you got another one?
Yeah, I mean, yeah, there's lots of examples. Another one as well for us is, like I said, digestion is the crux of the other technologies. And going back to material science, things we like using more and more are these platinum group elements, or things like, like rhenium and tungsten, and these kind of some of these materials you've probably heard a lot about on the news that are being used. They are cool because they're so hard, they're so dense, they're so strong. Also makes them very difficult to digest in acid. And when you just hit it with a laser and analyze it, it's very easy. We have no sample preparation. So that's a whole other world. We also do a lot of work in, polymer analysis or geology as well. So going back to kind of near and dear to my heart, mining and geochemistry has been ramping up a lot for us because so much of the story that I described, like even to a mining company, is in that mineralogy, is in that heterogeneity, and not just taking the whole rock and digesting it and getting like, okay, it has enough gold for me to go after if I'm Newmont, let's say, right? I want to know, where is that gold? What phase is it in? How is that going to affect the economics of my process of if it's in this sulfide versus if it's in this matrix over here, right? Or am I going to have environmental effects because, now if I'm having to extract the lithium from this mineral versus this mineral, well, this is going to cause a huge amount of rubidium to be in the system, and now the EPA is not going to like me. And so I actually don't want to go after that deposit. I want to go after this deposit.
For the first time, Dan Caruso pulls back the curtain in his book Bandwidth, a memoir that celebrates the pioneers who invented the internet's early backbones, the renegades who lit the fiber revolution, the antics that caused the biggest market crash of all time, and the new wave of entrepreneurs who led the industry back from its ashes. Though it seemed to happen in the blink of an eye, the Bandwidth adventure was a multi-decade roller coaster ride involving larger-than-life successes and devastating failures. The unbridled ambition of newly minted billionaires and high-profile tycoons created extraordinary value, unprecedented value destruction, and endless opportunities for a brave few. This reflects tech's past, present, and future, and is a story you won't soon forget. It will help you prosper during today's AI tech bubble. The book is available at dan-caruso.com/bandwidthbook and released in early 2025.
Wow. All right. So how unique is it, what you're doing? There are dozens of companies like you who have built these machines? Is the machines a good way to put it?
Yeah, machines, perfect. Yeah, instruments.
Or are you unique? Tell us kind of where you are in the spectrum of innovation.
Yeah, so we are the only company that is doing this, right? So there are a bunch of other, like obviously, the scientific instrumentation industry is one of the largest markets that people don't really think about. But, you have these, Goliaths like Thermo Fisher and Bruker and such that make all these different machines. So you can take a bunch of different machines and try to build an answer that our one machine gives you. So instead of like 3 or 4 different tools that you have to do a lot of different tests and a lot of work on to try to get the whole picture, we're the only company that can do this.
That sounds like a big deal.
Yeah.
But you're just really now perfecting how to do it in a reliable commercial sense. So you rolled out product number 1, took a bit longer, I know, as an investor than you would have liked it to. So what was version number 1? When did that come out? How's it working? What kind of reaction do you see from customers?
Yeah. This last year has been a really big year. Like what you were just mentioning. We were able to get a lot of early adopter sales. Kind of if you go with like the whole crossing the chasm architecture of a company, right? We got out there. We had this technology actually local here in Colorado. One of our first customers, and it's been a huge learning curve. As anybody in hard tech knows, it's never the things that you think.
I do want to talk about the hard tech meetups and stuff in the hard tech community.
Yeah,
in Colorado, we'll come back to that.
Let's do that.
Make sure we, remind me if I don't remember.
100%. Yeah. So as anybody in hard tech knows, it's integration is hell, and it's all the little things you don't think about that are going to bite you in the ass. For us, it's like vacuum compatible materials that we had to fight through so that we weren't damaging windows and all this kind of stuff. And so we went through a lot of product maturity over the past 2 years. So going back to your question, we deployed our first tool at kind of 2022 here in Colorado. So first deployed, and we've been, that instrument's been running now for over 2.5 years now, or two and some change, which has been great. And we now deployed in a bunch of different facilities, including national labs, academic institutions, private public partnerships, and industry, right? So even in additive manufacturing space. And we've learned a ton of just getting out there, getting customers using it, figuring out what breaks, why, what applications really we should be going after. And we should touch more on this point too, I think, from like a foundational company understanding of like when we were talking about applications, about building a tool to go find markets versus finding the market and building the tool, and looking at the funnel from different sides of that.
Yeah, and related to that, in the area I wanted to touch on, in fact, very related to it, is when it's really hard and expensive to do something, you do it a lot less frequently than when it's less expensive and easier. So, will you bring in kind of the level of both cost being done, turnaround time being down, so cost lower, turnaround time being faster, less resource required to do it? Will that lead to a whole bunch of new use cases that before would have been not worth even thinking about doing?
Yeah, in fact, that's the majority of our market, right? Is this whole space of, I'm not necessarily trying to go out and like displace Thermo Fisher in the markets that, people have been doing this technique for 30 years in. There's this whole unserved market that's kind of between these two instrument categories that we fit in. And is exactly what you're describing. It's all of a sudden people can now think about, I can see my lithium, I can measure my metals a lot faster and a lot easier, but I didn't have it in budget because I didn't know this existed, right? And so we've been in this whole kind of campaign for awareness of who we are, what we can do, and also validation in the marketplace, so that there's this huge adoption curve that's like, okay, well, now we're getting a lot of people putting us in their budget cycles. And now we're becoming when we're thinking about building a new lab, we should use a Massbox and not an ICP-MS. So that's really been a lot of what has been happening over the past couple of years. It's just the awareness of who we are.
Yeah, early on, you're somewhat evangelizing. I mean, there's a use case that already exists.
Yeah.
But now you're bringing kind of a new way to approach it. So, you've got to first kind of get the attention of those who might be interested. Then they have to believe your story, because if they don't believe your story, they're not going to try to see if it really works. Then they got to try it, and then when they get excited, they got to say, okay, now I got to go build a business case on why I should have one of these. And once that happens, over a period of time, that happens multiple times, then it starts to become more widely known, and it's a whole different market. But the first 3 years of trying to bring it to market, it's probably, there's a lot of hurdles you got to overcome.
Yeah.
Long sales cycle.
That's why everybody says hard tech is hard, right? And this is one of those things. It is giving through that like much longer chasm, let's say, just to keep using that terminology, than like you would have on a software side of things, where you can get a lot faster market adoption on something that's more quickly deployable, less capital intensive. These are big capital purchases. They're above a lot of signing authorities. So you have to have a strong story and a lot of market.
And a unit might cost roughly
$500,000.
$500,000. So it's a $500,000. It's not a $5 million, but it's meaningful. It's $500,000 commitment. You're selling it as a product, not there's a recurring services component to it. Yep. But in your business model, you're not saying ship us your samples, we'll do all the work for you. We'll sell you this piece of equipment, this machine. We'll teach you how to use it, and then we'll provide AI intelligence that layers in with that, right? AI intelligence to help figure out what's really going on when you run the process.
Exactly right.
So you're an AI store. You should be getting like a gazillion times revenue.
I think we were just on the back end of that. That's actually one of the big things. Like, for example, we're doing a lot of work with the Air Force and the Army now, is they want to be able to, there's a couple different stories there. One of them is, we have this aging fleet of stuff we don't even know how we made anymore. They don't even know what the material is. So they want to use our tool to say, what type of
I thought Afghanistan has all that stuff.
Sadly,
we leave
we
it
still
there?
do too. Our B-52s are still from 1960.
I know. Is that crazy?
Yeah, it's insane. And so, Air Force wants to be able to say, what kind of aluminum was this? And so we can, we're building in models that can analyze and build databases of all these materials and then be able to quickly tell you, hey, it's a 2024 with a high yttrium content or something. And so we're getting a lot of traction in the government side of things for doing exactly what you just described.
Yeah, no, it's very, very interesting. And as you think more broadly about because you're really early on. I mean, we're having this conversation as if you shipped 1,000, 10,000 units, but you're still very early. I mean,
we're unit 10.
Yeah, you're 10 is what you've basically shipped.
Yeah, we've built 10 units now.
Built 10 units. But they're getting in different hands, different use cases. You're planting some seeds, fertilizing them. You're getting going and learning what you could do, learning what the opportunity is to build a business around it.
Exactly.
But it's still very early. And what kind of reactions have you gotten from kind of the early use cases as customers have come back to you and shown excitement?
Actually, I want to tell us, like, this just happened to me last week. One of our customers is Los Alamos. And so we actually have 2 machines down at Los Alamos because we do nuclear work. I didn't mention that, but we can do really quick isotope fingerprinting for, is this enriched? Is it not enriched? Fingerprinting of isotopes and all sorts of cool stuff there. But all of a sudden, our 2 customers have been happy there, really engaged, a lot of feedback to us. They're publishing data now. And all of a sudden we just got this huge uptick in like 10 groups at Los Alamos. We're like, what is going on? So I just went down there. I was like, I'm going to go meet with all these groups and see what's happening. Well, an internal email went around that was like, hey, we have this we have this ICP-MS that we're going to give away for free because we got a Massbox now and we just use it all the time. And I was like, can I have that email? And they were like, no.
Please.
Yeah. So, that was an amazing, like, that's a win story.
Yes.
Right.
Huge.
Yeah. Like, you're going to throw away this, $400,000 tool because you like our box so much better. Like, that's amazing. So yeah, I love that story, but that happens too, even on the battery side with the researchers at SLAC and Stanford with Will Chu's group there. One of the biggest battery research groups for solid state batteries and electrolytes. They're just so excited because they've had all of these like hypotheses of like what their lithium's doing, how their battery's reacting, and for the first time, they can actually build a chemical image of exactly what's happening. Mm-hmm. So it's really cool to see people's eyes open into use cases that we would never think of. We had another customer that was having an issue with a certain analysis and they couldn't figure it out why on another technique. And then they threw it in the Massbox and they're like, oh, there's a bunch of zirconium in it. And then they're like, now they're going to publish a paper about using the Massbox for contaminant analysis. We're like, oh, thank you.
Perfect.
Yeah.
Yeah. So what do you think this could become? I mean, right now it's, the beginning of a niche market. What do you think you could grow this business to be? Whether if you look forward on your product roadmap, what might a version 2 be? What might version 3? What other ancillary services? And as you do that, maybe start by talking about how AI plays a role and how the recurring revenue model plays a role in the product and service that you offer.
Yeah. Okay. Let me start with the first part of that. Is I think the biggest thing that we do differently, like our technology obviously is like foundational to the Massbox and to, our first product and to what we're building. But we think about scientific instruments differently than anybody else in the marketplace, right? We're approaching it from, my generation of thinking that grew up with, going through not having cell phones to iPhones, and then all of a sudden like expecting a different experience versus like instruments that were designed in 1970 and 1980. And that's really what exists right now. And so fundamentally,
what exists right now is instruments literally from the 70s and 80s.
Yeah, they haven't changed very much.
Yeah.
And they either have their user interfaces. I mean, I still ran, when I was at the Mag Lab, I still ran on an instrument that ran Windows XP. Right. It's like it's a very behind world when it comes to user interface and experience. And why that matters is going back to the time component. It's like now you have scientists and professionals in industries that expect a tool to come in. They should be able to learn how to use it within like an hour and then just be off to the races and it's just up and working. And that ethos of the product design is not something that Thermo Fisher's doing or Bruker's doing. So when I think about like, where does this go? It's that, I want to establish the foundation of what an instrument should be. And the Massbox is that first product to show people that you can take things in the solid form now and get better and more rich data sets out of it for AI. We'll get back to in a second. Than you can by just digesting it in a bunch of acid and getting one number, right? So completely changing how you think about doing your analysis and empowering engineers to not think of mass spectrometry or analytical tools as a curse word they don't talk about. It's like, well, we send it out and we get a number back and we're happy. And now it's a tool that you can use to do your material science research, to refine your processes way faster and iterate that development cycle. And once it's in production, make sure that you're doing it the right way all the time. So taking that tool out of centralized labs, taking it out of academic institutions and putting it all over industry floor. That's our vision, is saying like, no, this is as easy to use as a ruler. This should be in your tool set no matter what you're doing. That's our vision. And, as far as like future products, there's a lot of derivative products and other markets that we can go after that are foundationally aligned with the ethos of the Massbox of make it easy to use, make somebody look at it like an Apple product and say, I want to touch that, right? I'm not intimidated by it. It's not like a bunch of wires coming out of it and, looks super sci-fi. It's like, no, it looks sexy. Like I feel like I could play with that. I feel like I understand what's happening.
Well, and even more than that, and I think this is true in your case, the physical product itself, you don't want to make it in a way where you have to be a scientist to operate it.
Yeah.
You want to, and I think you guys have done, where someone's got to go and take a piece of equipment and put it in the box. But then from there, you want to be able to, almost like a microwave, press a button.
Yeah.
It does what it does. And then what you're doing is getting the data feed and analyzing the data. So you've taken, the component of chemists who have to do a bunch of work physically on the sample. So you don't need to do that. You just need someone to load this up and then get the machine going. And then you need, expertise to analyze the results. Is that an oversimplification?
You don't even need the expertise to analyze the results, right? Like you should be able to be like, engineers and material science already know what to do with it. So you don't even need to be, or maybe that's what you meant by expertise. It's like that side of it. You don't need to be an analytical chemist. Yeah. You wanted to have the expertise on that side of things. And
who's doing the analytical chemist part of it?
Yeah, we are. Not you.
We are being, who's the we?
Exum, right? Like our company, our tool, we are the analytical chemists now. So you don't have to be.
Yeah.
You can get the data and do what you need to do with it, whatever that might be.
And how are you doing that? How are you, because that's starts to now sound like a service, right? It doesn't sound like you shipped a product. It's okay, here's your product, go do what you do. It sounded like you're saying, we'll take that data feed. Is that the way to do it? Think about it. We have a way of analyzing it and reading out to you the results of it so that you can then use those results to do whatever you're trying to do.
There's two layers to it. So one of it is just how we build the software foundationally, right? It's like the same way if you open up your iPhone, you're not a telecommunications expert, but you know how to dial a number.
Wait a second here.
Sorry, you are. Sorry. The proverbial you.
Yeah, okay.
not the.
I'm all 30 years wasted of my life.
Sorry. Everybody else on this. You don't have to be a telecommunications expert to understand how your phone works. You just know how to dial the numbers and press the big green button, and all of a sudden you're talking to your mom, right? Like how you build that software and the interaction is the foundational principle so that I can teach you to use the Massbox in an hour. But to your point, that the next tier down from that, from a service side of things, and it is something that we're building into an AI ML model, is being able to offer specialized software packages, like what I was talking about with the military, of being able to say, hey, you're going to run this, press go, and then have it analyzed by this model. And it's going to tell you exactly what material type it is. It's going to do the automatic quantitation for it. It's going to tell you like all of these different properties because we have this huge database now. Because we're the first instrument company that's starting out in this age of what it means to build a data set and to build things for AI ML readiness, right?
Yeah. It strikes me that, depending on what my use case is, okay, loading the material, in the instrument, straightforward. But there must be different. This is, I suspect, what you're talking about. Different ways you might want to test that material. I mean, do you want to test it? Do you want 50 sample size? You need to rotate it.
Exactly.
Are they little bursts? There's probably kind of a plan that you have because you're trying to discover something about that, and the right plan for one piece of material might be a different plan for another. So you're sampling kind of, what are you trying to accomplish and what sampling plan matters, and then how do you take the data and analyze it and tell you what the data says? It's almost like those are two related but different steps.
That's exactly where we're going with it in the next phase. Is you hit the nail right on the head there of going one step further with that sort of service offering, as the software side of things, of being able to say, you don't even need to think about, hey, should I do the raster size of this big, or how much laser power should I use, or what spot size should I use? Like, that's all going to be built into a model that's going to be able to basically determine all of that for you based on what it's analyzing. So it can do a little test sample. It's going to know automatically what category of material it's in. So it's, okay, this is a nickel. I need to use these laser powers for it. And it's going to be able to adaptively determine when do I hit a statistical robustness of the sample as it's analyzing, and just analyze just that amount, and do all of that automatically, so that you don't even need to think about it. Like, I'm just putting in the nickel and I get a number out that says it has this much iron in it and it's distributed this evenly.
Yeah, and will you, as part of what you do inside the company, will you be developing these kind of test plans and then the readouts? So, it's what they have to do is say, here's my use case. I press, this, sequence for that use case, or I, select, a particular use case, and then, but you guys have had to, work with them first, develop, okay, what are you trying to do? How are you trying to do it? Yeah, we'll be able to develop kind of the use case that, creates the sampling plan, and then we'll be able to kind of, give you the results of it. And then it's rinse and repeat after that. Or does AI help you figure that out?
So ultimately, that's like the ultimate path, right? Is like that, an AI ML model would be able to help us to figure that out. So the path to get there, though, is what you just described. It is making specific models to build more generalized models. So in the example of like the DoD, being able to do this automatic materials analysis and labeling and identification, takes the Air Force and Army coming to us and saying, like, here's all of our materials that we care about. We want to be able to identify these in anything that we put in there, right? Mm-hmm. So they're giving us a targeted database to build out, that they're giving us a contract to go out and do. And that's going to be the foundation for then tacking on a more generalized model of how we do things.
Gotcha. Which is kind of there's a professional services aspect of that. Exactly. And then there's just a recurring revenue.
Exactly.
Use the service to get your data feeds and get your analysis of what just happened. So there's both a hardware component and a software services component of what you're offering.
Yep, exactly.
Very cool.
Thanks.
Very cool. So how do you go from tens of units to hundreds of units to thousands of units? How does that happen over the next period of time?
The biggest thing, from that level of market adoption and what we're driving towards, really comes down around the recognition of like key industries, and then people within those industries trusting our technology, right? So we have like a lot of bigger deals now that we believe are going to be like the cornerstone deals of like, hey, when, I won't say the company names now, but when company A takes this technology, it's going to be a big signal to the marketplace of, okay, like, if they're doing it, we probably should do it now. Like, a lot of follow-on comes from those sorts of players. And it's because we've done so much work over the last 2 years to position ourselves in a really good place of strength to do that. Like getting certain certifications or getting a lot of publications or getting recognition where everybody's like, oh yeah, I've heard of Exum and the Massbox now, and you guys do that thing, and I heard about it from friends. And so this kind of like internal word of mouth marketing is starting to gain now, where a lot of people that should know about us are starting to know about us, which is great. So that's how we go from tens of units to hundreds of units to thousands of units. And then obviously not just focused on domestic markets, but going global with this, right? So, going into Europe and Asia and South America and expanding, right now, the blessing of the curse, like any startup, is we can analyze anything solid, which is kind of a lot of stuff. But if we try to do everything, we'll do nothing well. And so we have to maintain focus right now on specific key market pieces. And once we establish ourselves really well in here, and we can go back to hard tech here in a bit, hard tech's very sticky. Once you're in and you're like proven, you're going to last, right? And you're going to gain market adoption as long as you don't really screw it up. So, that's our focus is win these certain key markets and get a lot of level of stickiness there and continue to grow those. But then there's so many other markets that we can grow into and do the exact same playbook of focusing on segment specific work and becoming experts.
And by so many different markets, you mean use cases?
Use cases.
Example.
Yeah.
Yeah.
So like ceramics, like we haven't even like really touched ceramics, even though we know we have like a huge application there. It's like, okay, it's not the focus right now. Let's keep our head down.
Yeah, and certain industry verticals, certain use cases, kind of get those going. Hopefully choose wisely on the first handfuls of them and get that going, and then just layer in other use cases and other verticals.
Yep.
Yeah, it makes a ton of sense. And that's one thing as an investor that we have been excited about what you guys are doing is if you get this right, I mean, how hard is it to build one of these? I mean, it's hard to design and architect and get it to work, but once you've got that down, building many units, is that how tedious and it's consuming is that?
It's funny, like two of my engineers actually came from the automotive world, where we almost have as many pieces as you do it in like a small car in some ways. And so it's very similar to that, like you just said, like the initial design and getting that first prototype made or going through the validation builds, like it's difficult even because it's just simplicity stacked. Like nothing's like overly complicated. We're not trying to make, a quantum computer, for example. Like that's a whole
hard.
Other level of complexity. But it is like precision, right? And it is selecting the right materials and learning what materials are there. But once you have it dialed, this is something that a contract manufacturer is going to be doing for us, right? So it's something that we can scale the production of.
And does the contract manufacturing is plan to do that here in Colorado or do it
It's going to be elsewhere in California, actually. So keeping it in the States. So a manufacturer there that does scientific instruments.
Donald Trump will be proud of you to keep it in the States.
Hey,
so no tariffs for you.
Yeah, no tariffs. And also if you want to just keep funding going to certain areas, that'd be also great.
Well, that might be a little more problem.
So yeah, keeping it in America. And it is something that, you can get down to a science of how to build them, right? And a production line. And it's very measurable, and there's nothing that's, we're not trying to hold single atoms with lasers. So.
Yeah. And where within Colorado is your headquarters facility?
So we're in Denver.
You're in Denver. What part of Denver? I know I've been there. I should.
Yeah, it's remember. Like on the west side of it's Lakewood area, Edgewater, like right on the boundary there. Yeah, and that's actually like right where I live too. We love that area.
Yep. And tell us about hard tech in Colorado, in Denver, and in Colorado. What's the hard tech community like here? Are there gatherings, which I know there are?
Yeah.
Tell us about the gatherings. Tell us about the momentum. I'm going to have to, as a investor who wants you to raise more money, we're going to have to lose the hard tech is hard line because that's going to scare potential investors. I think there's a perception that if you're in hard tech, that it means it's really capital intensive. And what's been really interesting to me is a lot of the hard tech we're in, when you look at how much dollars really needs to go in, in absolute terms, it's small in comparison to a lot of these software companies, a lot smaller. I mean, you look at how much money you've gone through so far, it's not that much in the scheme of things. Now, you're still kind of rolling product to market.
Yeah.
But, the scaling of the product, when you get traction, is not going to require you to be, raising, tens of millions, let alone hundreds of millions of dollars, which is not kind of, you look at the software companies, they're doing $200 million raises. That's, there's something misleading about the capital intensity of hard tech that I think is not fully understood.
That's super important point, right? And I want to go back to that because I have a lot of thoughts on this. But to go back to the first part of your question is, when I went to grad school in Albuquerque in New Mexico, and when I was deciding of like where to start raising money and where I was going to like headquarter the business, it was like, initially you look at the coast, right? You look at San Francisco or Boston, something like that, or New York, maybe. And at the time, it was like, well, Denver kind of has this like up and coming startup scene, and decided to set everything up in Denver. And I'm so grateful that I did, because I don't think people realize like how much hard tech is in Colorado.
Yeah, a lot.
It's a lot. It's like and how many venture groups are not hardware agnostic, right? Like, or hardware like adverse.
Adverse.
Adverse. Sorry.
Hardware terrified.
Yeah, terrified. Yeah, I was like, that's what I meant to say. When you go to like San Francisco VCs or people that are traditionally software, they're like, oh, you make things, like we're out. Yeah. Like they just don't understand the model. So yeah, the hard tech community here is amazing, especially as a founder. There's a lot of other hard tech founders, people that have, and there are parts of hard tech that are difficult in different ways than software, but that doesn't mean that it's like harder than software companies or more risky or more capital intensive, like what you're describing. It's just different. And the ecosystem here has been really good for that. So yeah, we have meetups here. So if you're in the Colorado area, there are hard tech meetups. Me and one of our other board members and investors, Jim Thorson, put on a group every quarter called the Front Range Hard Tech Meetup.
I think Chris Ventures is going to sponsor one in Boulder.
Oh, awesome!
At least they ran it by me.
That's right. I forgot about that.
Yeah, the group ran it by me and asked for my green light, to fund something, and I'm like, yeah, let's do it.
So come on out. It's a lot of fun.
Do you know when the Boulder one is a date set?
I'll make sure that it's included for the notes for this. Or
yeah.
I'll get back.
These guys might be able to find it because they just ran it by me literally yesterday, the day before. So there might be a date already established.
Yeah. So if you're in the Colorado area, definitely come, especially if you're in hard tech or thinking about getting into hard tech. It's people that are literally thinking about starting a company, want advice. We always have really cool speakers there. And it's a lot of investors. It's a really just good networking event. And,
yep.
I've met some really awesome people through it. And then now actually there's another hard tech group that's starting as well that I can pull up, that's actually run by, I'm trying to remember it's a venture group and a bank that started putting it on all of a sudden. It's really cool. So it's starting to spread. And then, I know you've even done stuff in a lot of stuff with the quantum space. Yep. Of getting together a lot of those founders and, really done a lot
and
of
most of that's hard tech right now. There'll be a big software component to quantum, but a lot of the quantum that's being done here in Colorado right now is really building, just like you're building, kind of new devices, new equipment, new computers.
Everything from the cooling systems to the optics to the lasers to all of that is here in Denver and in Boulder. Yeah. It's really cool.
And space tech is, right now probably 80% hard tech and 20% software. And, and then there's a lot of more one-off stuff like what you're doing. There's, robots that cut your grass, robots that take care of your waste management. There's lots of variations of it. And they're, each one's its own interesting journey.
Yeah, 100%.
And I want to have Jim. I think I want to have Jim on the podcast too. I don't know him well, but his background seems to be very interesting, and he's very active in the community. And
yeah, Jim's great.
Yeah, at some point.
Yeah, I mean, Jim, he's fun too because he is a hard tech investor, seed stage, really early stuff. So he took a bet on us and a lot of other cool companies. Like he has a fusion company in his portfolio that's based here in Colorado, and
it's up north, right?
It's such a cool facility to go to. It's literally the only site that he could get that people would allow him to have like stray neutrons in. It was like a farm in the middle of nowhere. So it's like you would never expect it. It's like in the middle of farmland in this little cement building, and there's like a fusion reactor. So I mean, yeah, fascinating stuff. Actually, a lot of fusion stuff happening in Colorado.
Yeah, we're going to get a little closer to some of the fusion stuff ourselves because it's an exciting area, and we really have not even. I haven't even been in a meeting with someone who's been pitching us a fusion, but I think we have our first one scheduled already. It might even be the one Jim is involved with. I don't know for certain, but
Horn Industries maybe. Or?
Yeah, I think so. It could be.
Yeah, it's really cool. And I think going back to your other point, like we're seeing more and more venture groups either starting or having some amount of presence out here in Colorado, specifically focused on hard tech. And I think that's just going to keep growing, or should keep growing, because there's a lot of companies that are raising money here with really good foundational technology kind of for this next generation across the board. And so it's a really exciting time, and it's cool that Colorado seems to be at like the forefront of a lot of it. It's like Boston and Denver, like the two kind of epicenters for hard tech right now.
Really, I know they're epicenter for kind of your area of hard tech, but I wouldn't have thought of them as hard tech in a more general sense.
Yeah, there's a lot of good groups out there. There's a lot of companies like, let's say in my space or adjacent, like kind of instrumentation or like that, or a lot of biotech, let's say, in hard tech and bio. Like Boston has a lot of good stuff going on too. But yeah, it's a fun place to be in Colorado right now.
Good.
So
awesome.
Yeah. Oh, and then last point that I think you hit on, that is, I think, what people don't realize is they have this sense of like the capital required to build a mass spectrometer is going to take hundreds of millions of dollars. It's like, no, we did everything with like a fraction of that, right? Like we can be super efficient. We can really build foundational technologies for a lot less than people think, and a lot less than what software companies are raising. Like you're saying, like in the Bay Area for seed A and B rounds.
I assume this is something okay to talk about. If not, don't talk about it.
Yeah.
But the total amount of investment that's going to your company, not including non-dilutive capital, we'll talk a little bit about that, is
less than 10 million.
Less than 10 million. So getting product to market, haven't scaled it yet, but product market. But when your customers will start buying them, they're also giving you, not giving you, but paying, $500,000 a shot. And, a good part of that is some of that is cost of goods, but some of it is, is margin. And that then helps fund the business. And you don't have to sell, a million of them to make money. You start selling 100 of them, and all of a sudden it's like, that's
it's totally
already
different
adding
number
up.
Of games. Yeah. And you're not having to put in tens of millions of dollars into marketing budgets, right? And then having to do like freemium models and really just be bleeding so much capital for so long. And then, it's totally different. And people do have a distorted view of what it is to be a hard tech company. And they don't realize too, is that the really good thing about hard tech is that for the companies that make it through, and do make it past, to this adoption scale, they're really sticky. I mean, these are the companies that last for a long time. It's the companies that make something, right, and continue to iterate. And so that's really the core advantage to getting involved in this space.
And how much non-dilutive capital have you guys tapped in? A lot of the hard tech also is able to tap into sources of capital from kind of matching programs in the government and research grants, and that helps really develop the product without bringing dilutive capital in. Have you guys been able to tap into much of that?
Yeah, we're getting close to like $3 million of non-dilutive now. So that's SBIRs, maybe it's somewhere around that order of magnitude. With SBIRs, with actually Colorado programs for anybody founders in Colorado, OEdit as well. The Colorado OEdit program is amazing. One of the most unique things in the country right now. We've gotten $500,000 doing that program, and it's been so supportive. Helped us through a lot of stuff. And other grants as well. We've done stuff with NIST and all sorts of things. So, and they are a lot more, there's a lot more friendly, non-dilutive capital environments for hardware and hard tech than there is for like, let's say software.
Oh yeah, by a lot. Unless you're doing something really unique in software, I don't think that really, the parallel doesn't exist. So do you have visions in the future that there'll be need for kind of versions of the Matchbox that are far bigger, so that they could take far bigger samples, or is that just not a thing that would
Yeah, it's
be
interesting.
needed?
We've been approached for that actually by the Air Force. They're like, "Can we take a whole wing?" I'm like, "No." But, or something, even like somewhere in between those two scales. And the answer is, yes, we actually have some ideas of how can we make a gantry like system where you can kind of like analyze any surface.
Yeah, bring the material in a room.
Yeah, and then be able
Sorry.
to do yeah. So the answer is like, yeah, there are some unique things there that our technology allows for kind of some modularity of design for. So
Oh, that's interesting.
Yeah.
So look forward into the future and tell us what you think you'll be doing, 10 years from now. My guess is you're still going to be with what this becomes, what Exum becomes, as opposed to I'm going to sell and do something else. That's a guess, but maybe not. But what do you think your world looks like, personal world looks like on a professional side? You know, you know, well down the road, 10 years, not 30 years down the road.
Yeah, I think there's a really interesting. It's a really interesting time from what we're doing specifically in my little microcosm of like this whole new advancement of technology. And right now we're doing elemental analysis, and we're making it easier, and we're doing all things solid. But you have to remember there's like other phases of matter that people want to analyze, like the gases, the liquids. They want to be able to do organic analysis a lot easier. That's a huge pain right now.
What does that mean?
Organics are like the whole molecular analysis, so proteins or polymers, and understanding like, what do the chains look like, how much do they weigh, that sort of stuff. And a lot of that technology is also dated in a lot of ways in the software and the full ecosystem integration. One of the things that's really lacking is there is no equivalent in our space of like what Apple does. For better or for worse, I know there's a whole like Steve Jobs versus, Bill Gates approach to like open versus closed garden, type ecosystem, but Apple does a really good job of just integrating its product into one space. And there's never been more of like a clear need for that than in the lab, right? Because you get this sampling and you're tracing this material, and you might do 50 different tests with it. And you're having to kind of like pick pieces of software and different instrument companies and try to put all of this in together into one database. And it's terrible. And no instrument company is having the vision to say like, we should not only design our instruments to be better and to use, new technologies to make it faster, to make it smaller, to make it cheaper, more efficient, but design the software packages to be like an iPhone, and then integrate all of everything from our scales to our instruments together into one, environment, so that we can actually build a true data set for materials, right? Because it's going to be becoming exponentially more and more important for everything that, you're involved with, from the quantum world to silicon manufacturing to kind of all the new materials that need to happen. It's going to get so complex that only AI is going to be able to deal with it, right? And so you want to be able to feed this as much data as possible, everything from the mass spec side to the rheology to, whatever it might be, into, as many dimensions of a data set as possible. And doing the physical science is super important, as much as it is to build the models of like, how can we theoretically design something? We need to have that closed loop system of theoretically design something with AI, manufacture it, measure it, close that loop of data.
Yeah, and you're mentioning AI, which certainly plays a big role in that. But one of the big promises of quantum is that the approach of quantum computing will be able to discover new materials, new molecules that otherwise we have to hope we stumble across as humankind, versus the quantum computing approach is able to just solve for them.
Yeah.
Okay, here's a brand new material that does all these crazy things that you could have never used even an AI-based computer to figure out it existed, that will feed with AI, but you're right. Then it needs to feed with the physical world itself, which is so. And I think there's also a lot of use cases talk about that are space related too. That in zero gravity, you'll be able to do things to create new materials. And then there's, as you were saying earlier, there's new materials that exist out there on different, celestial bodies that, we are going to be able to both discover and not just wait for them to happen to drop on Earth, but maybe bring them back here. Maybe even need to test them, on the moon, test them on Mars, and, find, okay, here's some helium-3, for example, that is the kind we're going to waste a bunch of money, spend a bunch of money shipping it from the moon back to Earth. Let's make sure what we're shipping is as concentrated or as ideal as it should be. So, you could see that there could be an explosion of use cases for I'll say both the devices you're building, but also the talent and intellectual property that you're developing within the company as well, in order to test and analyze the materials. So, there's certainly a path forward. I believe that you guys could build a blowout company that that is extremely significant and one of the big success stories of Colorado.
Well, thank you very much, and we always appreciate your support on everything. So,
thank you. Well, thank you. This has been fun. I feel like I know you better, and I certainly know the company a lot better. And I've said this in a few other podcasts. One thing I enjoy most about doing these podcasts is I get to know people at a level that I don't otherwise would take so much longer to do. Because even if I went out to 5 dinners, I probably wouldn't learn as much about you at this level as I can in a conversation like what we just had.
Yeah, I definitely appreciate it. I enjoyed this. So thanks for having me on.
All right, good deal.
Yeah.
Thanks.
Cheers. Thanks, Dan.
All righty.
Thank you for listening to this episode of The Bear Roars. If you enjoyed the episode, please like and subscribe on your listening platform. This podcast was produced by Loud Bear Productions and edited by Courtney Caruso with support from Kendall Weinberg, Emily Reed, and Gibson Siegert.